Hello, everyone. Thanks for staying awake this late in the afternoon. I'm going to give this talk, which is interesting. It's basically stuff that I've been looking at for the last 6 months, and I just kind of want to disseminate some of the information that I learned. There will be some actionable takeaways at the end, but as you're going through this, you might not really get these like tangible things that you can apply to your application. So if you're looking through this and going, I'm not really sure how I'm supposed to interpret this, wait till the end and I'll have some kind of like concrete tidbits of how to avoid all of the stuff that you're going to see that we dig into. Just a few things. The slides will of course be posted online, so I get asked a lot of time about how I like dig into these topics, and so I'm showing a lot of like command line tools that I use to find out this information. So you really don't need to pay too close attention to what they are, just know that they'll be in the slides for future reference. And then I'll also have links to all the tools that are being used at the very end. Okay, we'll start with a little quiz. It's a multiple choice question. How many methods are in this piece of code? So 0, 1, or 2. You probably immediately have like a gut reaction, and like an answer that you pick. Maybe it's 0, maybe it's 1, maybe it's 2. I'd be interested if you actually think it's 2, but let's take a look and actually kind of see if we can answer this question. First of all, there are obviously 0 methods inside this class. I've written no methods in the source file, so it's perfectly valid to say that this class has 0 methods. Of course, that would be a really uninteresting answer to this problem. So let's start taking our class through the build pipeline of Android and see what comes out. So we take our contents here, write it to a file. We use the Java compiler to take the source code and turn it into a class file. And then we can use this other tool from the Java development kit called JavaP. And this is going to allow us to see inside the class file what was compiled. And if we run this on our compiled class, we see that there's actually a constructor inside our example class. We didn't write one in the source file, but Java-C has taken the liberty of adding that constructor automatically. So this means that there's actually one method in this class, both 0 in the source file, but one method in the class. This is not where Android builds stop. In the Android SDK, there's a tool called DX, which does dexing, which takes the Java class files, turns it into Android's Dalvik bytecode. And so we can run our example class through dex. And there's another tool in the Android SDK called dexdump, which will give us a little information about what's actually inside these dex files. You run it, it's going to print out a bunch of stuff. It's like offsets into the file and counts in its various tables. And if we look closely, one of these things stands out, and that's the method table inside the dex file says that there's actually 2. Well, that makes no sense. Unfortunately, dexdump doesn't give us an easy way to look at what the methods are. So in response to that, I wrote a little tool which will actually just dump methods inside of a dex file. And if we do this, we see that it does return 2 methods. It returns our constructor, which we know the Java compiler created, even though we didn't write one. But it also says that there's a object constructor. Certainly our code is not calling new object everywhere. So where does this method come from that it winds up being referenced in the dex file? If we go back to the JavaP tool that prints class file information, you can actually give it some additional flags to look more deeply inside what's inside classes. Here I'm passing -c, which is going to decompile the bytecodes into something that's a little more human readable. It looks like this. Don't worry if you don't really know how to read this. The important thing is at index 1 here, it's our constructor, our generated constructor, is calling the superclass constructor. And this is because even though we didn't declare it, example extends from object, and every constructor has to call a superclass constructor. So it gets inserted automatically. And that means, well, there's actually 2 methods from our class file. All of these answers actually were correct. So no matter what you saw, you got it right. It's like some new wave kindergarten where everyone's Everyone's a winner. So the difference between these, though, is terminology, and it's kind of where they live. So that we didn't declare any methods. But really, only humans care about this. As humans, we read and write these files. We're the only ones that really care what goes in and out of them, the order, and that's not really relevant for the rest of the talk, but I had to include 0 to make the joke complete. So the other two are the ones that are really more important. The number of methods that are actually compiled in the class file. These are the methods that actually, declared or not, are inside that class. And then the two methods are the number of methods that are referenced. And this is this is inclusive in the sense that our own methods that we wrote are counted, and also all the other methods that are referenced from within those methods. So if I'm calling out to, Android's logger or whatever, that log.d method that I'm referring to counts against this reference method count, which is what's in the dex file. And this is what people traditionally refer to when you talk about method count on Android, because dex has the infamous limit for the number of methods that can be referenced. Okay, so we saw a constructor being created without us having declared one. So let's go look for some other hidden things that are generated that we might not have known were there. Nested classes are a useful construct. They're actually not in Java 1.0. They came in a later version. And you see stuff like this for when you're defining an adapter inside of a view or presenter. And so if we compile this class, this is one file with two classes, one nested inside the other. If we compile this, we see that actually two separate class files end up on the file system. If Java had truly nested classes, we would only get one class file. We would get itemsview.class. But there's not true nesting in Java. So what are actually in these classes? Whoops, that was a little too fast. In the itemsView one, the outer class, all we have is the constructor. There's no reference, no hint that there was an inner class. If we look at the contents of the nested class, you see that it has its implicit constructor, and you kind of know that it was inside an outer class because its name got mangled. Another important thing to note, if I go back, we see that this itemsView class is public, which is what we declared in the source file. But the inner class, the nested class, even though it's declared as private, it's not actually private in the class file. It's package scoped. And this makes sense because we had two class files that were generated, and they're being generated in the same package. And this, again, just further proves that there's no true nesting in Java, that it effectively is this. Even though you're nesting those two class definitions, you're effectively just creating two classes that are next to each other in the same package. And you could do this if you wanted to. You can actually use that naming scheme as two separate source files. The $ is a valid character in, for names in Java, methods or class names. However, this is really interesting because I know that I can do stuff like define a private static method in the outer class, and I can refer to that private method in the inner class. So the outer one is private, and we're referencing it from the inner class. Now that we know that there's no such thing as true nesting, though, how does this work in our hypothetical separated system where our item adapter class needs to refer to the private method in itemsView? So this will not compile. However, this will compile. So what's going on here? Well, we can go back to our tools. We can use Java-C again. I'm referencing, I think, TextView, so I had to add the Android APIs to Java. And now I'm going to print out the contents of the nested class to see what method it's calling. And if you look at index 2, it's not actually calling the display text method. It's calling this method access $000, which we didn't define. So is that actually in the itemsView class? If we look, it is. We see our private static method is still there, but we now have this additional method that we didn't write automatically being added. If we look inside the contents of that method, all it does is forward the call to our original display text method. And this makes sense, right? Because we need some way to call this private method from a package scoped class, and so Java is going to synthesize a package scoped method to facilitate that method call. If we go back to our separated example, our manual example, we can make this compile in the exact same way. We can add that method, and we can update the other class to refer to it. And so, like I said, the dex file has this limit of methods. And so when you have these methods that are going to be added based on the ways that you're writing your source files, those can actually add up. So it's important to understand why this is happening. Well, we know why it's happening. We're trying to access a private member somewhere that it really can't work. So you might say, well, you only did Java-C. Like maybe the dex tool can see that and automatically eliminate that method for us. So if we compile our two classes that are generated and list them out, you can see that that's actually not the case. The dex tool just compiles it like it was any other method. So it actually does end up in your dex file. You might say, well, I heard about this new Jack compiler, and the Jack compiler takes the source file directly and directly produces dex files. So maybe it can do something where it doesn't need to generate this extra method. And there's certainly no access method. However, there's this -wrap0 method, which is effectively the exact same thing. There's also a tool called ProGuard, which probably a lot of people are using. You might say, well, ProGuard should be able to take care of this, right? So I can write a quick ProGuard keep. I can run ProGuard on our class files and print out the methods. And I get this. So the constructors were removed because they weren't being used, so I'm just going to add them back in because normally they would stick around. You'll see that the access method is still there, but if you look closely, our display text method has disappeared. We retained the access method, but display text disappeared. So what the hell is going on here? You can actually just unzip the jar that ProGuard produced, and then we can go back to our Java P tool and look inside the ProGuarded class file. And if we look at the access method, it no longer is calling display text. ProGuard has essentially taken the contents of display text and moved them into the access method and then deleted the display text method. This access method was the only one referring to that private method, so it just inlined it because no one else was using it. So yes, ProGuard can kind of help, but it's also not guaranteed here to be able to do this. We got lucky because this is such a trivial example, but this is certainly not guaranteed. You might think, well, I don't really nest classes that much, maybe it's a handful, so if I'm only getting a handful of these extra methods, it's not really a big deal, right? Well, let me introduce you to our friend, the anonymous class. Anonymous classes behave the exact same way. They are effectively the same thing. It's just, it's a nested class, but it has no name. And so if in these listeners, which we use all too frequently, you reference a private method in the enclosing class, that's going to generate a synthetic accessor method. This is also true for fields, and I think this is the one that's probably a lot more common. We have fields in these outer classes, these activities that we're modifying the state of inside of these listeners. So I've done like a completely awful implementation here, but what I'm doing is I'm setting a value. I'm using a pre-increment, a pre-decrement, a post-increment, a post-decrement, and then the log message has to read the value from the field. So how many methods are we going to get from this? You might say, well, maybe it's only two, maybe one for reading, one for writing, and then the increment and decrement kind of get turned into reads, increments, and writes. If only. Oops, I got sweet highlighting. If that was only the case, we compile this, and one method is being generated for each of those types. So if you think that in an activity or fragment or wherever, you have 4 or 5 listeners, you have maybe 10 fields that are private in the outer class, you're getting a nice combination of explosion of accessor methods. So you still might be unconvinced that these are a problem, that there's a lot of these. You say, well, maybe it's 50, maybe it's 100. Is that really a big deal? Turns out we can find out, oh, these are what the the numbers at the end correspond to like the operation. So to is always writing a field. So we can actually find out how prevalent these are in the wild. These commands will actually pull every APK from your phone, every app that you've installed that's a third-party app. We can write a script which it just uses this dex method list and then just greps all the different numbers. Don't like worry about reading that. I'll put a link to it at the end. And then we can run this crazy command, which basically is just going to go over every single APK that I pulled off my phone, run this script, and then make a nice, pretty table. And we can actually, and it sorts it. It sorts it by the most accessor methods by package name. And for my phone, we're in the thousands, the multiple thousands. The Amazon's, one of the Amazon apps. Amazon actually makes up 5 of the top 6 here, so if that's interesting. But these are in the thousands, right? The top ones are in 5,000 synthetic accessor methods. 5,000 methods, that's an entire library. That's like an AppCompat. You have an entire AppCompat of just literally useless methods that only exist to be jumping points to some other method. Also, because we kind of looked at ProGuard, like obfuscation is going to screw with these numbers. Inlining is going to screw with them. So they're not like, don't take them as like the exact number. It just puts you in the ballpark of realizing how many methods are actually made up, how many methods are in your application that are these useless accessor methods. By the way, Twitter at the bottom here, they have 1,000. They're programming their app, so there's probably a lot more. But I thought it was interesting because they're the lowest number of reported methods for the highest number of actual methods. They have 171,000 methods in their app, and only 1,000 synthetic accessors that remain. So that was pretty impressive. So we can fix this. This is easy to do, right? We just have to not make something private. We have to make it package scoped when we're referencing it across those boundaries. IntelliJ has an inspection for this. It's not enabled by default, but you can go in and search for private member, which is fun to search for, and it will take it will take our example and it will actually highlight it yellow, and you can option enter on it, and it will give you an intention action to just take that private member that you're accessing and make it package scoped. And so when you think about these nested classes, try to think of them as siblings instead of having like a parent-child relationship. You can't really access a private member from an outer class. So you have to make it package scoped. And like this is not going to cause problems, right? Because even if you're a library, hopefully these people aren't putting classes in the same package as you so that they can access these things that you're making more visible. I also put in a feature request for a lint check for this, so hopefully in the future you could potentially fail your build if you're doing this. And I've been going through a ton of open source libraries and fixing these visibility problems so that the libraries themselves don't impose hundreds of extra methods. This is actually super important for libraries that do code generation. We were actually able to reduce the number of methods in our application by 2,700 just by changing one of our code generation steps. 2,700 methods for literally for free for generating something that was package scoped instead of private scoped. So these synthetic methods, they're called synthetic because you didn't write them, they were generated automatically for you. These accessor ones are not the only ones. So generics is another thing that came post Java 1.0, and so it had to be kind of retrofitted into how Java works. And so we see this a lot in libraries and even in our own applications. We're using these generic interfaces because they're extremely convenient and they allow us to retain type safety. If we just have something, a method that accepts a generic value, when you compile this, you're actually going to find that every method that that accepts that generic is going to get turned into 2 methods. One that accepts string, or whatever the generic type that you're using is, and one that's just object. And this is like what erasure is. So you hear a lot of people talk about erasure, you might not kind of understand what's happening. This is like the manifestation of erasure. We have to generate code that only uses object because that's what is going to end up being actually called when you reference this generic method. If we look at what actually goes in that extra method, it's just a cast, so it casts to your type, and then it calls the real implementation that accepts the generic. And so anyone that's calling, this call method is going to dispatch to this object method. Their calling code is going to pass in whatever their object is, and then this code has to cast it and call into the real implementation. So every method that uses a generic winds up turning into two methods. This is also true of return values. So if you have a method that's returning a generic, we basically see the exact same thing. Two methods get generated, one that returns, in this case, our view, and then at the bottom, one that returns object. This one's a lot more simple because it doesn't have to really do anything. It just accepts the view and then re-returns it as an object type. Another interesting thing to note here, which a lot of people don't realize that this is a feature of the Java language. If you have a method that you're overriding, you can actually change its return value to be a more specific version of that type. This is called a covariant return type. And it doesn't even have to be, like in this case, we're implementing an interface. The base class doesn't even have to be, it doesn't have to be an interface or anything. You could just be overriding a method from a base class. You can change its return type to be something more specific. And the reason that you would do something like this is if you had other methods in our second class, which had to call into this get method, and they want the implementation type, not the more broad kind of in this case view type. It will allow them to do customizations that were only specific to text view because they're in that class already. So covariant return type. I'm sure you can guess what happens here. We get yet another method. So in this case, it's both a generic and a covariant return type. So we've taken our one method and turned it into three by basically not doing anything. This is a Python script that detects these. This took a long time to figure out, but I wanted to see, I really didn't know how prevalent this was in applications. And so we can go through the same process and run it over every phone that every app that I at least had installed. So it's in the thousands, low thousands. There's not a whole lot you can do here. I showed that ProGuard can kind of help. The advantage of this case is that if ProGuard can detect that no one is actually referring to the generic version of the method that takes object or returns object, it can actually eliminate that. So you will see like hundreds or thousands of these can be removed by ProGuard, but some of them just can't because you are using them in the generic sense where you're calling the method on the interface or whatever. So that one's more interesting to try and figure out. The kind of last example that I want to look at here for methods deals with something that's new and upcoming in Android, which is the Java 8 language features. So we've had retro Lambda for a while, but now the Jack compiler is also implementing these in the same spirit, which is allowing them to be used in a way that's back portable. But is there an associated cost to these new language features? I just have a simple class which says hello when we call its method. And what I want to do is basically take my greeter and make it say hello on this executor. So executor has a single method called run, and it accepts a runnable. In the current world, we would make that greeter type final, and then we would just create a new runnable and call the method directly. Lambda world, it's just reducing the verbosity of doing that. This will still create a runnable, but it does so kind of implicitly. You don't have to specify the type. You don't have to know like the actual method name, the argument types. And then the last one is method references. These are a little more interesting because it basically infers that this is a method that returns nothing and accepts no arguments. So I can turn that into a runnable automatically because I know all I have to do is call that method. So that's fun, but how much do these cost? What are the costs of applying these language features? So I set up retro Lambda toolchain here and a toolchain using Jack. Neither of these are using ProGuard or minification in Jack's case because it doesn't affect the results. Okay, and I'm also comparing two versions of retro Lambda. So in the anonymous class case, the case that we've been using for so long, it's always two methods. So if we compile our example, we see that this is our anonymous class assigned a monotonically increasing number here. We see the constructor. The constructor is going to take in the greeter class for us, and then it has a run method, which if we decompile it, all it does is just call the method. This is exactly what we expect, very straightforward. But now let's get into the interesting ones. When we do a Lambda, if you're using an old version of retro Lambda, this was like really expensive. That one little tiny line of code could be 6 or 7 methods to just produce that functionality. Thankfully, the current version is down to 4, and Jack even bests it with 3, so only one worse than the anonymous class. But what's the difference? Why is there that extra method? Well, we know how to figure that out. This is retro Lambda, which actually has 2 additional methods, and the one that's new is the top one. What's happening here is you're defining a block of code inside the Lambda, and that code has to go somewhere. It's not encoded inside the method that defines the Lambda, because that would be weird. It doesn't belong to that method. It has to be stored somewhere so that it can be passed into whatever you're calling. And so that's what this top method is. It basically just copy pastes whatever you write into the Lambda into a method on that same class. And you can see the implementation here. All it does is just delegate to the say-hi method, very similar to what our runnable implementation did. We still have our constructor, we still have our run method, except here the run method is different. Instead of calling greeter directly, it's going to call back into the original class and call that Lambda method. And this is the extra method. Here's where retro Lambda screws it up. For some definition of screwing it up. Instead of calling the constructor directly to create this generated class, it actually generates another method, which is just a static factory method, which just calls the constructor. So I would love to get rid of that someday. There actually is an issue for it, so hopefully we'll see that disappear, because the migration to Jack is not exceedingly simple for various reasons. And so it would be great to have them kind of on par so that people could start using these language features sooner rather than later, regardless of whether they can migrate to Jack. And then Jack's basically the same thing, except it doesn't have that additional static method. We still get the Lambda one, although it's named kind of crazy, and then the generated class is named very creatively with the entire type signature in the name. But that's it, so 3 methods. So Lambdas basically cause that additional method at the top to be created, and so that's why they cost 1 additional method. Method references are also really interesting. So retro Lambda and Jack are essentially tied. Retro Lambda sometimes has to generate an extra method, and that's because you might be referring to a private method. And so it's actually not retro Lambda generating it. Java generates one of those synthetic accessor methods, because if you're passing a private method, if you're passing a reference to a private method to another class, it's going to have no way of actually calling that. So that's what the 4th one is. Jack, interestingly enough, generates 3 for every single method reference, but it should be generating 2 for every single one except for that private case. And in that case, it should only be generating 3. Currently, it generates an accessor method for every single method reference. And so there's a bug filed for that too. So hopefully we'll see Jack get down to 2 methods. And that's really important because that puts the method reference on the same par as the anonymous class. It makes it a 0-cost abstraction from switching from the anonymous class to the method reference, which would be really nice. Lambdas, unfortunately, will likely never get down to the same amount. And the reason that will never happen is that you also could be referring to like private members or private methods inside of the Lambda. And so it can't just like copy that into the generated runnable, because again, it doesn't have any way of accessing those things. We can count these as well. So let's look and see how many lambdas are kind of being used in the wild. Same deal. Oh, by the way, I forgot to say, this takes a long time. It's like 10 minutes probably. It also depends on how many apps that you end up pulling. So if you wind up doing this yourself for whatever reason, don't get impatient. It will take a long time, but you will get a result. Unfortunately, apparently not a lot of people are using Lambdas, and I was excited to see that we pay the most. Our application, we pay the most. We have 826 Lambdas, which means and that's the number of Lambdas, not the number of methods. And so the number of methods that we have from our Lambdas are 826 times 3 or maybe 4. So, do like 3 times 3.1 or something. No one's using Jack yet, or at least of the applications I had installed, no one's using Jack with Lambdas. They might be using Jack and I just couldn't, not using Lambdas, which would be weird. Or additionally, they could be proguarding. So again, this proguard completely hides these Lambda classes and names of the methods. So like, if you're a popular application using Lambdas and you proguard, that's probably why you're not on this list. Or I just don't like your app. Okay, so that was all about methods. And before I move on, don't look at that. The reason I was looking into this was, one, to stave off the 65K, hitting the 65K limit. But those methods have a runtime cost as well. There's cost for loading the additional bytecode, and there's also cost for just the extra trampoline that you have to go through when you're executing them. So the private field one is my favorite because a lot of times you see that happen inside these anonymous listeners. And those are usually running as the result of a UI interaction on the main thread. And so what you don't want is a computationally expensive piece of code that you have to run on the main thread, whether it's for animation, size calculation, whatever. You don't want those, every single time you're referencing those fields, you don't want to be jumping through that extra method. Looking up a field is fairly fast. Invoking a method and then looking up a field is still going to be fast, but it's 100% of the time going to be slower than just looking up the field. You're introducing these indirections, which you're not going to get you're not going to be like dropping frames all of a sudden because these accessor methods exist, but they're like literally useless methods that the only thing they serve to do is bloat your APK and very, very subtly slow down your application. So I'll have some tips at the end about how to get rid of them. But like that IntelliJ inspection is kind of the best one. Like, just turn it on, see where they're at. And it's especially important in libraries because as a library, you want to have the most minimal impact on the host application. Okay, so I want to change gears a tiny bit and talk about something a little more runtime focused. And that has to do with collections. So if you have anything that resembles the following in your application, you're probably wasting more resources than you should. Android has these specialized collections, which I think most people nowadays know about. And the implementation varies, but they're specialized to these cases, which are very common, which is like when you have an integer index into a map referring to some value. So there's a specialized collection for that. And a lot of times people talk about this in the context of autoboxing. So what autoboxing is, if you're not aware, if we have this hash map which accepts an integer key, say you have an integer of some value and you want to put a value in this map, or conversely, you're iterating over the entries and you want to get the value from a key, this conversion isn't just straightforward. It has to go through an additional step called autoboxing, which is where it takes the primitive value and turns it into the class version of that, which in this case is integer. The bottom one's not that expensive. It's basically just like kind of unwrapping a type. The top one is the one that's bad. For small numbers, there's a cache, so it's not bad. But if you have just like a random slew of integers, it's actually going to be allocating objects every single time you call a method, which is generic and accepts the big I integer. So this is what most people talk about as like the big advantage. And it's very true that this is a big advantage, but it turns out there's two other big advantages which aren't really talked about a lot. The first one is really just data indirection. So if you look at how a hash map is implemented, it has an array of these nodes, and then it keeps its own size. And when it has to find when you're either putting a value or looking up a value, it has to jump into this array. And this is the hashing step. So this is still, it's a cache that's constant time. This is the constant time operation where it finds the hash and then does the offset into the array. However, this is an array of nodes. The node type has both the key and the value. It also has the hash, and it has a pointer to an additional node. And if you've ever heard the term hash collision, actually we'll see that in the next slide. Forget I said that. But again, we got to the array, we found the reference to the node. We have to jump to the node now, and then we have to look inside the node, and if we want the value, we get the reference to the value, and we have to jump to the value. We basically have to go through these indirections, and they're kind of in all different spaces in memory. So you essentially have to like make these jumps in memory in order just to get a value for a single key, or to put a value at a single key. And then it can get worse. This is the hash collision problem, where if two items hash to the same bucket, hash map will degrade into what is essentially a linked list inside that bucket. So if we happen to hit this case, we now have to walk the linked list and find the matching exact hash. And I'm going to look at Sparse Array. So Sparse Array is the replacement for this one here. I'm going to look at that in a second. But before we get there, the other advantage really just comes around to overhead, the overhead in memory of these collections. So we have two classes here. We can actually use a tool called Java Object Layout, and it's going to tell us what the overhead of creating one of these objects is in memory. We'll run it on HashMap. It's going to print out a bunch of stuff. It basically is just showing you the cost per field. The important number is here at the bottom, where every instance of a hash map, just the hash map, not the nodes, not the keys or values or anything, just the hash map object itself is 48 bytes. So it's not bad. That's small. We run it on the node object. Same stuff. We see our 4 fields. This one's 32 bytes. And so it's 32 bytes, but it's 32 bytes for every single node in that map. So every item in that map, every key and value pair is going to be inside one of these nodes. So it's essentially 32 times the number of entries. So we can use a formula like this to figure out what the actual size of an object is at runtime when I start putting values into it. This is not fully correct. You also have to account for things like the array. There's an array that has to hold the nodes, so we need to account for the space that array has to occupy. And so this is kind of complicated. It's basically 4, which is like a single integer, which is the reference to each array, multiplied by the size of the array. The problem is HashMap has this thing called a load factor. Oh, and the 8 at the end is like a constant overhead for every array. But HashMap has this thing called load factor, which it never tries to be completely full. It tries to maintain a certain percentage of fullness. So when it reaches that percentage, it's going to, like an array list would grow. The HashMap is also going to grow so that it can maintain some empty spaces. And the reason for that is because if that doesn't happen, you start getting a lot of collisions and a lot of degradation in performance. So this would be approximately the value that a hash map with however many entries and whatever the load factor is. We could figure out how many bytes in memory this is going to occupy. And by the way, the default load factor is 75, so 75%. So HashMap tries to say 3/4 full at all times. Okay, so Sparse Array. Sparse Array is what you should be using if you want to replace hash maps like this. So let's look at the 2 cases we looked at in HashMap, which is the indirection, the like levels of indirection, and the size in memory. Sparse arrays stores two arrays that are siblings. One is just the keys, the other is the values. So if we're looking up a value in this map, or putting a value in this map, the first thing we do is we go into this integer array, and unlike hash map, it's not actually constant time, so it has to do a binary search inside this array. We can then jump to the values array, and in this case, the binary search gave us the exact cell in the values array in order to look up the value, and because that array is the values, we can then return, jump directly to that reference and return that back to you. And so there's a lot less indirection here in terms of memory. The integer array is contiguous. There's no linked list. We can jump directly to inside the values array, and there's no node object that we have to unwrap and then get to the value. So there's a lot less indirection. However, it does come with that slowdown of not being perfectly constant time. And so this is why you want to keep them for relatively small maps. And that's, by small, it's like in the order of hundreds of entries. So if you get into the thousands or whatever, the performance of the binary search is going to cause it to be so slow that the overhead of hash map is probably starts looking pretty appealing in terms of performance. Memory overhead, just by looking at this, I mean, the simplicity of it, you should imagine that it's going to be less. And you're right. Unfortunately, this tool, I forgot to mention, I'm running this on, it's giving you the values for like the JVM, not Android. But in this case, because the classes are exactly the same, and the JVM is 64-bit and Android's now 64-bit, the numbers should be translatable. If that bothers you, treat them as an approximation and allow for some 20% variance or something. It's certainly a lot easier than figuring out how to get the object sizes on Android itself, which is not impossible. It's just a lot easier this way. Okay, so the object itself for Sparse Array, a little bit smaller, 32 bytes. That size really doesn't matter. What does matter, however, is obviously, these aren't just 32 bytes. We have the entry problem again. So we have to account for the array, that is the integers, for the keys, and that's essentially 4 times the number of entries, actually plus 8, which I forgot. And then there's also the array for the values, which is the same thing, 4 times the number of entries, plus 8. And so what's different here is that there's no, Sparse Array doesn't have a load factor, but it kind of does implicitly because these arrays are, they're trees, they're binary trees. And so they're not filled, they're not contiguous. There's spaces inside of them that are unoccupied. And so we kind of have to account for that with a little fudge factor, which is essentially similar to the load factor. And so in this case, and it totally depends on what data you're putting into the map. So in this case, I'm just kind of using the same value. I'm assuming that these arrays are going to be about 75% full, which is a pretty safe assumption. And so now we can make a direct comparison against these things. We know that we can count the indirection jumps, that's easy. And now we can use these equations to compare the actual values of memory that these instances would occupy. So I'm going to use 0.75 again for hash map, which is the default. And we can pick a value for the number of entries. In this case, I just picked 50. Maybe it's a map of states in the United States. And then we can run these computations. And what you see is that effectively the sparse array is a third of the size. And you have to remember there's a slight performance overhead to this because every operation is no longer constant time, but it's 50 elements. And so the number of searches in the binary tree is going to be very fast. All right, so that was a lot of stuff. And it's kind of hard to parse that and come away with well, I have Android Studio open, what do I do now to take this and actually apply it to my application? It turns out that there's actually some extremely trivial to-dos in order to avoid these overheads, both at compile time with methods and runtime for the overhead of various objects and the indirection that they may afford. The first one I already showed. Turn on that private member inspection and listen to it. Don't ignore it. You don't have to do it for every single type, but if you see one, we just kind of do it as we go. If you see one, Alt-Enter, enter, and it'll fix it for you, and then move on. You don't need to go through and kind of do it all at once. It's something you can do as you go in your app. Conversely, for libraries, it's a little more important. Like I said, just as a library, you should be wanting to minimize your impact, both in APK size and runtime performance, or deck size and runtime performance. So if you have a library, you might want to go through and find all these. Oh, that was this. If you don't want to contribute to these libraries by sending a pull request, just report it as a bug. This should be treated as a bug in libraries. There is no reason for these synthetic accessor methods to exist in libraries. It's a waste of space in the dex file. It's a waste of time in the runtime. Report them as bugs. If you are using Retro Lambda, please, please, please make sure you're upgraded to the latest version, because you are wasting probably thousands of methods. And if you're writing an open source library, maybe just suck it up and deal with the anonymous classes. It's not that big of a deal, but again, it goes back to the fact that you just want to have the minimal impact for you application developers, so that you're never the problem as the library. Try out Jack. It's a big deal. It's still undergoing rapid development. It's missing a lot of things that are going to make it applicable to everyone here. But certainly there's going to be applications which are more trivial or not doing anything exotic at build time. And don't ignore bugs. Don't switch. Find it crashes and be like, whatever, I'll try in 2 years. You can do that. Just report the bug before you switch back to Java-C and Dex. Because this is the future, and you can cover your ears and close your eyes, but it's happening, so better to find these things sooner rather than later. And then just turn on ProGuard. ProGuard helps out here. Whether using ProGuard or there's the new shrinker, which is incremental and so it works with instant run and presumably will be what Jack uses as well. Don't use overly matchy rules. If you ever see ** in a ProGuard rules file, that is wrong 100% of the time. That is never what you should be using, because you've effectively just nuked any advantages that you were getting from ProGuard. You're saying that yeah, I'm pulling in OKHTTP, but I don't want all of these methods from HTTP2, which I'm not even using. I don't want them to be stripped. I want to retain them just in case. It's not smart. If you see these on open source libraries, that is a bug. Report that as a bug. And if you have those in your own app, try and figure out why they were initially there. Take them out and actually think and look at the failure of ProGuard and see if there's something more specific that you can change your rule to. It's a very complex topic here. Probably doing ProGuard correctly is deserving of its own talk. So, and additionally, there's been a few talks both by people at Google at I/O and third parties at various DroidCons that you can watch as well. If this stuff is really tickling you and interesting you, there's a few other presentations that you can take a look at. I gave a talk about a year ago. It focused on for loops and string builder and kind of the overhead that's in them, very similar to the collection stuff. I have a link. All slides will also be published with these links. The DEX file format, Jesse Wilson gave a 7-minute talk about what's actually in the DEX file format and how it's structured. 7 minutes, super quick. And then the exact opposite of that is a 3-hour talk from Chet and Rahman from a few years ago at Devox. And they also really dive into the runtime cost of objects. And there's the link. Okay, links to the tools. There's the bug for Jack generating the extra method references. Go be don't comment, but go star. Hopefully with Retro Lambda, there's a bug filed for that too, so we can make it on par with Jack, because that would be nice. Like I said, everyone can't switch right away. The Dex method list tool that I wrote, this thing will suck in class files, jar files, AARs, dexes, and APKs. and print out the list of referenced methods, which is super useful for not only finding these synthetic accessors, but from where all your methods kind of are being allocated. The Java Object Layout tool, this one's super advanced. I can't see many people using this. It was just kind of a shortcut for me. And if you want the scripts that I used for counting the various resources in the APKs, I put them on GitHub on a gist. And at 48 minutes into the talk, I am completed. Thank you.